All right. So yesterday we introduced the concept of electric current and the idea that we're going to be, for the next few chapters, talking about a charge as it moves around and needing to develop the language for talking about charge as it moves. So
This chapter 20.
it is chapter 20. So again, we have the definition of current, and current was defined as the rate that charge flows past a point, where delta Q is the amount of charge that flows past you, and T is the time that it takes for that charge to flow past. It was measured in units of amperes, where an ampere is defined as a coulomb per second. And we went through the Drude model of conduction, where we found that if you had a wire, the current was related to something called the drift velocity. And the idea is that inside that wire, there is some fraction of the electrons, not all the electrons. Most of the electrons are tightly bound to their individual atoms, but some fraction of the electrons are so loosely bound to individual atoms that they can hop easily from place to place. And they're the ones that move around and cause current. And if you look at the average velocity of those electrons inside the wire, we call that the drift velocity. And the faster those electrons are moving, the more electrons per second go past you. So there was a relationship between the current and the drift velocity. And it was driven by the fact that when you apply a voltage and therefore create an electric field inside your wire, those electrons are going to have a tendency to accelerate. And so they pick up some speed and they travel through your wire. But of course, they can't pick up speed forever. They keep whacking into things. So they'll speed up for a while, whack into something and stop. Speed up for a while, whack into something and stop. And so what's going to happen is this drift velocity tends to be a constant value. And we found that for an applied voltage, the larger the voltage you apply from one side of the wire to the other, the larger the current that you get. And the constant of proportionality that related those two things was the resistance, where the resistance so those are all the concepts that we ran through the other day. We introduced resistance, which is a measure of how difficult it is to push that current through the wire. When the resistance is large, the current you get for a particular size voltage is small. But when the resistance is small, you get a lot of current for a not very big voltage. And the distinction between this and this was this is the resistance. This is for a particular wire of a certain size and shape, whereas this thing that looks like a scripty P, which is actually the Greek letter rho, is called the resistivity. And the resistivity is determined not by the size and shape of your wire, but just by the material. It's going to be a function of the microscopic interactions of the electrons inside that wire with one another and with the atoms in the lattice. And so some materials are going to have a low resistivity. Those are going to be things that are good electrical conductors and can pass current through them quickly and easily. Whereas other things will have a comparatively high resistivity, those are going to be things that are like electrical insulators, where it takes a whole lot of voltage to push much current through them at all. And we know that resistivity is itself related to things like the scattering time of the charges inside the wire, all kinds of stuff that I'm not going to make you guys memorize. And also the charge carrier density. How many of those electrons inside the wire are freely able to move? Because if there's a lot of them, that's going to tend to create a larger current than if you have only a handful of electrons that can move from place to place and carry current. So the thing that I want to center in on now is this concept of the resistivity, because for most materials, that resistivity is reasonably constant. In fact, if you look in chapter 20, there's a chart where it's going to plot out the resistivity of different kinds of metals by number. And again, that number tends to be fairly small. It's measured in a unit ohm meters. This is resistivity. But in spite of the fact that that chart in your book suggests that it's constant, it's not completely constant. Because what's going to happen is the resistivity of material can be affected in one way or another by the temperature of the material. One way to think about why that is, you imagine I've got a wire made up of a bunch of atoms. And of course, all those atoms are positively charged. And every atom has electrons bound to it, but the lowest energy electrons, they're basically stuck on their individual atoms. They can't move from place to place and carry current. They're the electrons that are stuck in those lower energy levels of your atom. But then the more loosely bound electrons, the ones that are out here at the higher energies in higher orbits, if you want to imagine electrons as orbiting like little planets, which isn't terrible. These are the ones that can hop from place to place and carry current. So if they hop around, current is going to flow in my wire. And what's going to happen is the higher the temperature of your wire, the more you're changing which states are occupied by your electrons. So what can happen is, maybe if I get this particular wire hotter, what's going to happen is some of these electrons that are down in the low energy states and they can't move from atom to atom, they'll get enough energy to move to a higher orbit. And when they do, they'll hop up here to those higher orbits, and now they can hop around themselves. So the charge carrier density N might get larger when you heat your wire up. So if that's the case, a wire that's like that would tend to have a resistivity that would get smaller as you have more electrons moving around. However, it's not necessarily that simple, because sometimes what happens is, let's say you've got an electron where there's or an atom where there's already a lot of electrons that are in those higher levels. And maybe there's only so many orbitals that can be occupied there. There's only so much space in those higher level orbits for electrons to go. Well, if that's the case, if you heat that particular metal up, then what's going to happen is maybe one of these electrons in the lower orbits hops itself up to this higher orbit. And now what's going to happen is there's so many electrons in these higher orbits that if an electron from this atom tries to hop to this atom, there's no place for it to live. And so what's going to happen is, because it's so crowded in those upper orbits, by increasing the number of electrons that occupy those higher energy orbits, sometimes you actually decrease the ability to conduct electricity, because you reduce the number of opportunities that other electrons have to fill those little holes where electrons used to be. And so, depending on the nature of your material, the temperature of the material could make the resistivity go up, or it could make it go down. And the way that we're going to model that is with this relationship. And all this really is kind of an experimental phenomenological model to sort of help us deal with the temperature change of resistivity. And here's the idea. Imagine I have a wire, and at that wire, I measure its resistivity at a particular temperature, some reference temperature. Usually that reference temperature is about 20 degrees Celsius. So let's let T naught be our reference temperature. And I measure the resistivity at that reference temperature. And that particular resistivity is what I call rho naught. Now I take that same piece of wire and I heat it up or cool it down. I change whatever temperature that object has, and I heat it up to some different temperature. So this is the new temperature that I heat it up or cool it down to. Well, at that new temperature, I'll get a different resistivity. So this is my new resistivity. And this little thing right here, the thing that looks like a fish, that's called the temperature change coefficient of resistivity. And it's just a number that is unique to each type of metal. And in fact, in that same chart where you could find the resistivities of different metals in your textbook, you'll also find in that same chart, they show you the temperature change coefficients or coefficients of resistivity for those same materials. And what you'll find is that for some of those materials, alpha is positive. In other of those materials, alpha is negative. And to see what this means in practice, look at what's going to happen in this formula. Let's say that you heat up your metal. So that means that your new temperature is a bigger number than your old temperature. Well, that means that this term right here in parentheses is going to be a positive number. I'm going to take a big number minus a smaller number. So this is a positive number. Now, let's say that alpha is also a positive number. So that means this times this is going to be a positive number. And it'll probably be a fairly small positive number. However, now inside the brackets here, I have 1 plus a positive number, which means inside the brackets, I would get a positive number that is bigger than 1. So this would tell me that my new resistivity is going to be my old resistivity multiplied by a number that is larger than 1. So if alpha is positive, if you heat the object up, the resistivity is going to get bigger. Now, by the same reasoning, if I had alpha that was a negative number, then heating that material up would mean this thing is positive because this is bigger than this, but I'd have a positive number times a negative number, so this term would be a negative amount. A negative number plus 1 is going to be a number that's less than 1. And so I'd be taking this term in brackets would be a number less than 1 times my original resistivity. I would get a number that is smaller. So if alpha is negative, heating the wire up will cause the resistivity to drop. And there are plenty of materials for which that kind of behavior happens. So it can go either way. But that's the basic idea. And the way that you would use this function is as long as you know the resistivity of the metal at one temperature, you can use it to figure out the resistivity at some different temperature. That's the way it functions. Any questions about that? Now, why might I care about something like this? Well, if you've used any piece of electronics for a period of time, one of the things you've probably noticed is that those things tend to heat up. Like your laptops are probably especially bad about getting really, really hot. Because what's going to happen is in a wire, as you pass through electrical current, here's a bunch of atoms. And if your charge carriers, the electrons, are zinging around and going for a while, hitting an atom and slowing down, and then zinging a while, hitting an atom and slowing down, going for a while, hitting the atom and slowing down, what's going to happen is every time this electron collides with an atom, it's losing some of its kinetic energy, and it's transferring that kinetic energy to the atom. The atom starts to rattle around a little bit faster than it used to be rattling. And that would be an increase in temperature. And so sending current through a wire tends to raise the temperature of that wire, and changing the temperature of the wire tends to change the resistivity. And so if I were someone who was designing a circuit, I might need to make sure I know the resistance of different parts of that circuit. However, as the temperature changes, that resistance will also change. And so a lot of times when people are designing electronics, they have to be careful to make sure that it stays within a temperature range that doesn't cause the resistances to change too much from what they expect. And when they do, they may end up with poor behavior or poor performance. It's why sometimes your laptop, if the fan doesn't work properly, it might overheat, because as it gets hotter and hotter and hotter, all of a sudden, there are elements inside your electronics that don't have the resistance that they're supposed to, and all of a sudden, they start to perform poorly. One of your homework problems has you, I think, choosing a material based on making sure that this resistance doesn't change from this resistance more than a certain percentage, so that you get the sort of performance that you're expecting to get. That's why we end up caring. We also can sometimes use this particular bit of physics to help us figure stuff out. Many times, even in biology, you'll need to know the temperature of something. And of course, how do we typically measure temperatures? Well, traditionally you'd use thermometers, and wasn't a thermometer, but usually a small column of alcohol or mercury. And what happens is that column of alcohol or mercury expands or contracts as it gets hotter or colder in a reliable way. And you use the length of that column to determine the temperature. But sticking a thermometer in something is not always the easiest thing to do, given the various geometries that you could have for an experiment. And so sometimes you have to be able to measure temperatures using different methods. One method that I've used many times to measure temperatures is take a small piece of material that has a known resistivity and then measure the resistance across it. And as you heat it up or cool it down, the resistance might change. So, when I was in my graduate school days and I had to measure the temperature of things that were very, very close to absolute zero, the traditional thermometer wouldn't work, because if I stick a traditional thermometer in, a tank of liquid helium at 4 Kelvin, that mercury inside the thermometer would just freeze. It would solidify and freeze. Plus, I wouldn't be able to see it because it's inside the bottom of a thermos and I can't read it. So instead, what we would do is we'd put a resistor inside and we'd measure the resistivity of that platinum film resistor. And since we knew the temperature dependence, we knew that every time the resistivity changed by a certain amount, that was corresponding to a certain change in temperature. You can use that as a quick and dirty thermometer. So there's lots of ways that this piece of physics can be of use to us. The next big thing that they talk about in chapter 20 is the concept of power. One way to think about it is that as these electrons move around from place to place, and they pick up kinetic energy and then lose it to the atoms, and then pick up more kinetic energy and lose it to the atoms, there's a transfer of energy from the electrons to the material itself. And sometimes we need to know how much energy that is. And that's where we want to introduce the concept of electrical power. Now, power was a concept that we introduced back in chapter 7 during physics 1. And we didn't do a whole lot with it at the time. We just kind of mentioned it and moved on with our lives. But power was defined as the amount of work done over time. That's the definition of power. Now, work had units of joules, and time, of course, is measured in seconds. And so a joule per second has a name. It's a watt. So if I have a 100-watt light bulb, that means that I'm transferring to that light bulb 100 joules of energy every second. That's what it tells me. Now, to see how I'm going to connect power to the idea of electric current, it helps to think about units, right? Remember, power is measured in joules per second. Now, when I think about electrical circuits, the two things that I tend to think about most frequently are the electric potential, or volts, and the electric current, or amps. Now, a volt is a particular unit, and a volt was defined, remember, from the definition of potential as U over Q. So this had units of joules per coulomb, right? That's what a volt is. It's a joule per coulomb. Now, by the same reasoning, the definition of current was delta Q over delta T, which means that an ampere of current had units of coulombs per second. And the thing that becomes kind of obvious to me is that if I were just to take a voltage and multiply it by a current, well, I'd have joules per coulomb times coulombs per second. And if I multiplied those two things together, the coulombs would cancel and it would leave joules per second, which is a watt. So it turns out that the power delivered to a wire can be deduced just by thinking about units. Turns out that the power is just going to equal the current that you put through your wire times delta V. Conceptually, that should make a little bit of sense if you think about it this way, because if you imagine, if I'm thinking about power, the amount of energy that I get per second is going to depend on two things, right? If I'm getting delivered that power by these little charge carriers as they move past, there's two things that happen, right? I tells me how many of these electrons there are every second. If I is really big, I've got a ton of charge carriers, a gazillion charge carriers going past me. And of course, the more they go past me and start dumping their energy in the wire, the more energy I'm going to get. So I is about how many electrons are flowing past me. Now, V is about how much energy each electron has. If V is big, each one of these electrons has a bunch of energy, because remember, the volt is a joule per coulomb. It's energy per charge. So if V is big, each electron has a ton of energy. If V is tiny, each electron barely has anything. It dumps off a tiny bit of energy. So that's why it works out this way. This is how much energy each electron has. This is about how many electrons there actually are. And together, that's going to give me how much energy I get per second. Now, unfortunately, just thinking about units doesn't tell us the entire story, right? As you certainly know by now, I'm very fond of problems that require you guys think about how a quantity changes in response to some other kind of change. And so if I were to look at this and ask you, hey, what would happen to the power being delivered to, say, a light bulb if I doubled the voltage of the battery that light bulb was connected to? Now, what's going to happen is the way a light bulb works, at least your traditional incandescent kind, you got the little screwy part. Inside, you've got two little thin wires and a little curly filament connecting the two. And of course, that is usually encased in a bulb of glass. Now, why does it work that way? Well, what's going to happen is when you screw that light bulb in, what happens is you send current in through the little bottom of the bulb, and then that current goes through the bottom of the bulb into this wire here, through the little curly guy, that's called the filament. And then out the other side, and then it comes out through the side screwy part. That screwy part is like connected to the interior, so the current comes out the other side. So you get a flow through the bulb and out again. Now, the reason that your light bulb lights up is because the resistivity of the screwy part, the bottom part, these little wires here, is so small that it might as well be zero. However, the filament is made out of a different material. And the material that filament is made out of usually has a much, much higher resistivity than all the other materials. Often it's tungsten or some sort of carbonized thread, something like that. But it's usually something with a much higher resistivity than everything else. And remember, the resistance of a wire depends on a couple of things. The resistance depends on the resistivity, the length of the wire divided by the area of the wire. And notice we're making the filament out of a material where rho is big. That's going to tend to make R pretty big. We're also making it out of a material that's super loopy and curly, right? If you were to take all those little curly wires and stretch them out, they would be quite long. So by making them super curly, we're often able to make this length exceptionally long because we're going to pack a huge length of wire into a tiny amount of space. It's also super, super thin wire. Super thin wire is going to have a small cross-sectional area. So this is big, this is small. All these things together tend to make R really big. And since for ohmic materials, delta V equals I times R, that's going to change the amount of current that I get inside this wire. Now, if I double the voltage, you might think, oh, I'm going to double my power. But the problem is, if I change the voltage, I'm also going to end up changing the current. And so it's not as simple as saying, oh, I can double this and therefore double this, because when I double V, I'm also changing I too. I can't change one without changing the other. And so to get a full handle on how this is going to work, I need to be a little cleverer than that. Because one thing that's not going to change if I hook this light bulb up to a bigger battery is the resistance of my filament. Well, that was determined when I built the light bulb to begin with, right? It was determined when I chose the material, or when I chose the length of the filament wire, or the size of the filament wire. All of those things can't change once the light bulb is built. So maybe what I want to do is substitute out this expression and replace it with something that has R in it rather than I and V. Well, one way I could do that is, since V is equal to I times R, I can replace this V with I times R. So I'd have I times R. So an alternate way of expressing the power would be I squared times R. Now, you'll notice if I write it this way, if I double how big I is, I know R is not going to change, but if I double how big that is, that factor of 2 that I increased it by has to get squared. It'll come out not 2 times bigger, but 4 times bigger. But I could have gone the other way as well. Remember, if delta V equals I times R, if I rearrange that, I can get that I is delta V divided by R. So what if I, instead of replacing V, what if I replaced I instead? I'd have delta V times delta V over R, or delta V squared over R. And you'll notice that even here, it becomes obvious this way as well. If I double how big my battery is, that factor of 2 gets squared, and it's going to come out 4 times larger. So what we end up with are 3 different equations for the power being delivered to an electrical circuit. And which of those 3 equations you use is going to depend on what information you have available to you. If I told you that I've got a 100-watt bulb, and I want to find the resistance of that 100-watt bulb, well, the reason they call them 100-watt bulbs is because they'll deliver 100 watts when you plug them in here in the United States. However, in the United States, all the standard plugs tend to be wired at 120 volts. That's pretty much the standard. So yeah, it's 100 watts, but only if you're using a power source that's 120 volts. So for that 100-watt light bulb, I know the power, P, and I know the voltage it's intended for, V. So I know P and I know V. Maybe I want to find the resistance. Well, if I know P and I know V and I want the resistance, this equation will get me my answer. What if I knew P and I knew V and I wanted the current? Well, here's P, here's V. I can find the current. So what's going to happen is which of these is useful at a given moment in time will depend entirely on what information you have and what information you don't have and are looking to figure out. So pick the appropriate one. Pick the one that has the information you need in it, but avoids anything else you don't know. Just like back in chapter 2 last semester, that's going to be your approach to figuring out the power in an electric circuit. So in terms of concepts, chapter 20 is pretty light. This is pretty much it. We've pretty much blazed through the vast majority of chapter 20. But for my money, chapter 20 is kind of just the appetizer for the main course that is chapter 21. Because chapter 21 is going to take all these concepts and it's going to force you to use them to figure stuff out. And that's where most of the circuit stuff is really going to come into its own. So what we're going to learn in that chapter is how to understand what's going on in an electric circuit. So I think we saw a little bit of this in the capacitance chapter, but just to remind you, when we draw circuit diagrams, there's symbols that we tend to use. And this symbol of a long line next to a short parallel line, when you see that symbol, that's a battery. Now, let's imagine this battery here has an EMF, it's a voltage of 12 volts. Come on, Roscoe. And I'm going to connect this battery to some piece of wire where the resistivity is non-zero, which we will call a resistor. So a resistor is just an element of my wire that has a non-zero resistance. It'll get denoted on circuit diagrams as a little zigzaggedy line. Now, the wires in between, we're going to generally assume are perfect conductors. In other words, we're going to imagine that for this wire right here, if you know that the resistance of that wire is rho L over A, we're going to imagine that rho is basically about 0. Now, in the real world, it's obviously not 0. It's pretty small, though. But what's going to happen is this resistivity is so small, we're going to basically ignore any resistance in any of these wires. But this little guy right here, rho is definitely not 0. And therefore, we have some amount of resistance. Let's say this resistance is, I don't know, 10 ohms. Now, obviously, if I do that, that's going to draw current. I would see electric current come out of my battery. And since this is the positive terminal, that's the negative terminal, the current would always be flowing from the positive terminal to the negative terminal. And therefore, it would travel through the resistor into the battery. And of course, the little elf inside the battery always replaces the charges as they move out. So I would get a constant flow of a certain amount of current. How much current? Well, obviously, I would use Ohm's law. And if I wanted to know what that current was, I could take the voltage across it, 12 volts divided by the current through it, and I'd have a whopping 1.2 amps. So if only life could be that simple, where every problem would be this easy, everyone would get A's in this class. We're going to make it more complicated. So what would happen if I were to take this circuit and snip it with a pair of scissors right here? So now I've got a little gap right here. Well, now what's going to happen is if I tried to send current out of this battery, well, what's going to happen is the current would hit a dead end over here. And if that's the case, any charges that build up down here would cause kind of a traffic jam of sorts, and nobody behind it could move either. And as a consequence, if I have this gap in my circuit, this is what we call an open circuit. I would get no current. And in fact, when you flip a light switch, what you are literally doing is creating a gap in your circuit that current cannot flow through, and that's why the lights go out, right? And in fact, what happens is usually you have, instead of a straight up gap, you'll have like a little pivoty switch thing where, you know, this can rotate and close the circuit, or rotate and open the circuit. So when the gap is open, there's no current, the lights are off. When you flip the switch and connect a path across that gap, now current will flow and your lights are on, right? That's what we call an open circuit. So if you cannot have a complete path from one terminal of your battery back to the negative terminal of your battery, the circuit doesn't do anything at all. There can be no current flowing if there's not a path all the way through it for your various elements. Now, what about if I did something like this? Imagine that I've got here's a battery. It's connected by wires, but there's no resistors anywhere. Well, what's going to happen right there? Well, I know that Ohm's law says that V equals I times R. Let's say that V is 12 volts, but my R is 0. Well, if I go to measure for my current, what's going to happen is my current would be given by this, right? But when I try to plug in 0, I would be dividing by 0. Now, what does it mean when you divide by 0? In math, dividing by 0 is undefined. In physics, what does it mean when you're dividing by 0? Well, dividing by 0 is basically infinite. So what we'd be saying is that if I divide by 0, I basically have infinite amounts of current. So what's going to happen here is when I close this up, my battery tries to provide an infinite amount of current. Now, an infinite amount of current it can't really do. And in fact, what will end up happening, if you look at it here, if I plug in R equals 0, I get delta V equals 0. And you might think, well, what does that even mean? Well, if I'm trying to send so much current out so quickly, remember what's happening in my battery, right? My battery has, in our parlance here, a little elf, and that little elf has one job, and it's to grab bits of positive charge at his feet, move them up here, and replace them with negatives. So when he grabs a positive, moves up here, he puts positive there, leaves negatives behind. Positive here and negatives behind. His job is to keep these charges separate so that the voltage across that battery is always a constant, let's say 12 volts. But what happens is as the current flows through the circuit, these positive charges, they flow out and they come over here and try to cancel out those negatives. If the elf did nothing, all these positive charges would flow through, cancel all those negative charges, and the voltage across my battery would drop to 0. Because the little elf is doing his job, or in the real world, because the chemical reaction in the battery is doing its job, every time one of these charges comes through and cancels one of those out, the chemical reaction just replaces them to keep that voltage the same. But there's a limit to how fast that reaction can occur. And in the case of 0 resistance, the current is so large that this cancellation happens so fast that the voltage of my battery would start to drop to 0, right? This, what we call right here, is called a short circuit. Right? A short circuit occurs when you have a path from your positive to your negative terminal of your battery that travels through 0 resistance. And if that's the case, the current that it tries to draw is effectively infinite. And what's going to happen in the real world is that when you have infinity current going through your wire, and remember that the power being delivered to a wire goes as I squared times R. And in the real world, the R of your wire is very close to 0, but it's not quite 0. And if I take infinity squared, it's super huge, times even a tiny number gives me a super huge amount of power. So literally what happens is the power being delivered to this wire is so large that it tends to do things like melt your wires, catch them on fire. Most electrical fires occur because you accidentally make a short circuit when you weren't supposed to. And so they can be tremendously dangerous. Never, ever do this. Never connect your one terminal to the other terminal of your battery across 0 resistance, because it will cause things to catastrophically fail. Now, I do say that if you've ever done this, it's kind of cool. Take like a piece of steel wool from like your kitchen and lay it across the terminals of a 9-volt battery. Now, what will happen is every time you touch the steel wool to your battery, you're creating a little short circuit. But what happens is it sends current through your little bits of steel wool, and the steel wool is so thin that it will almost instantaneously get hot and melt, and just you'll see it like spark red and kind of burn away to nothing. So you probably won't catch your house on fire doing it, but it looks really cool. So try that at home, kids. Just do it over the sink or something. But that's a short circuit. And so when we deal with electricity, we're almost always looking at what we call closed or complete circuits, places where we have a path from your positive terminal to your negative terminal that allows current to flow. And in a situation like this, where this positive terminal is always 12 volts and this negative terminal is always effectively 0, the current will always be flowing in the same direction. We would therefore refer to this kind of circuit where you're using a battery that's constant as a DC, or direct current circuit. All that direct current means is that the current flows in a consistent direction. Let's make it more complicated. Let's take a direct current or DC circuit, and let's have that DC circuit operate in the presence of multiple resistors. So now we've seen this sort of thing before back in chapter 19, because any current that flows out of this battery has to travel first through that resistor, then also through that resistor, and back again. It's a complete circuit, but these two resistors, because they're connected in such a way that any current going through one has to go through the other, are connected, as we say, in series. Right? We saw the same thing with capacitors in the previous chapter. So I want to know how to find the equivalent resistance for two resistors that are in series. And we're going to apply the logic the same way we did when we did this with capacitors. The way it'll work is like this, right? Let's say I've got this battery, and for convenience sake, let's say the voltage across that battery is 12 volts. Now, what's going to happen is the electric potential will change anytime there's an electric field. And what's going to happen is inside the wires, these perfect conducting wires, the resistance is so low that if I try to set up an electric field, what's going to happen is the charges will just move around. And they'll move around until they cancel out that electric field. And as a consequence, what's going to happen is inside a perfect conductor, the electric potential will never change. I'll only get a change in potential if there's resistance inside that piece of wire. So if this is, let's say, 12 volts right here, when I go right here, there can't be any change between there and there because there's no resistance in between. So this is also 12 volts, still 12 volts, still 12 volts, still 12 volts. Now, when I go across this resistor, however, there could be a change in potential. The potential at this end of the resistor will be larger than at this end of the resistor. So across this resistor, there will be what I'll call a voltage drop, delta V1. So let's call this 12 volts, delta V total. And what's going to happen is, if this is 12 volts, when I get to here, it'll be something a little bit less than 12 volts. But then it'll be the same, the same, the same. Then I'm going to go across this resistor here. There'll be another drop in potential, which I will call delta V2. Now, can't be a change, can't be a change, can't be a change, can't be a change. And now I'm back to the battery. And we can always call the negative terminal of the battery effectively 0 volts. What that tells me is that I started off at 12 volts, I dropped 2 times, and by the time I was finished, I was down to 0. So that relationship allows me to conclude that for this circuit, delta V total has to be equal to delta V1 plus delta V2, right? If I started off at 12 volts and I ended up at 0 and I only dropped twice, then this drop plus this drop better, by God, add up to 12. So That's a useful conclusion to draw. Now, the second thing that I have to think about is the current, right? So the current is the number of coulombs per second that go past me. And the analogy that I like to use when I'm thinking about these circuits is I imagine that these wires are like roads, and the charge carriers inside the wire, the electrons inside the wire, they're kind of like cars on the road. Now, these roads are special in that the traffic on these roads are always bumper to bumper. Because look, even if there's no current flowing in these wires at all, the wires are still full of electrons, right? The wires are full of the cars, and the cars are always there. And it's just that sometimes the cars are sitting still because there's no current. And other time, the cars are moving past me really, really fast because there's lots of current. So I'm going to think of current as like the number of cars that go past me on the road. But what becomes obvious is that if I look right here and I count how many cars go past me on the road, and I see 10 cars going past me on the road, and it's bumper to bumper the entire way, then I know that somebody up the road a bit, if they don't see 10 cars going past them per second, we have a problem. Because if 10 cars go past me per second, but they're not going past this person per second, where did the cars go, right? Cars can't just vanish. And if they're already bumper to bumper, I can't crowd them in any closer. So what that tells me is that for this particular geometry of circuit, if I have a certain amount of current up here, I got to have the same current everywhere else. Whatever current flows through this battery or this resistor, the same current would have to flow through that resistor. And that allows me to draw the conclusion that the current that goes through resistor 1 has to be the same as the current that flows through resistor 2. And for that matter, it has to be equal to whatever current is flowing out of my battery. It's got to be the same at all points around that loop because there's no place else for that traffic to be diverted to. Now, if I've already drawn those two conclusions, and I know that Ohm's law must be in general true, then I can require that Ohm's law be true for the first resistor. So delta V1 has to equal I1 times R1. By the same reasoning, delta V2 would have to equal I2 times R2. And heck, we're going to imagine replacing these two resistors with an equivalent resistor. And if I replace these with an equivalent resistor, I would have had the battery and then that one equivalent resistor. And that would imply that delta V total, this battery, would have to equal I total times R total, where R total is the equivalent resistor that I'm trying to replace these guys with. So if I take these two conclusions that we drew, combine them with these ideas, here's what we see. Well, if delta V total is I total R total, I can replace that. So I have I total R total. If delta V1 is I1 R1, I1 R1. If delta V2 is I2 R2, right, that equation has to be true. Except we just said all three of the I's are the same thing. But if these are all the same thing, they're going to all cancel. And so for resistors in series, the equivalent resistance is just the sum of the individual resistances. Just add them up. If I had added a third resistor, all that would have happened was I could have added a third term or a fourth term. I could keep going forever. Just as long as they're in series, you just add them up, and that's your total resistance, and it's super easy. We can do this in our sleep. So you know where I'm going next. If this is the equivalent resistance rule for a bunch of resistors that are in series, there's probably an equivalent resistance rule for resistors that are in parallel as well. What would that rule look like? Well, let's draw a circuit that's in parallel. Here's my DC battery. Here's resistor 1. Here's resistor 2. That's V total. You notice this is also a complete circuit because I could go from the battery and I have a path to return to where I started. And in fact, I have multiple paths I can take. I could go through resistor 1 or I could go through resistor 2 instead. Either way, it provides a path to ground where the current can flow. So I will definitely get some current. However, when I think about this in terms of voltage drops, imagine that V total is, say, 12 volts. So it's 12 volts here, it's 12 volts here, it's 12 volts here. There's no changes because there's no resistances. 12 volts here, 12 volts here. Now I'm going to have a change as I go across resistor 1. And so it's going to be lower here than it was here. However, if this is V equals 0, it can't change, can't change, can't change, can't change. So right here, it's got to be 0. So it went from 12 all the way down to 0. That tells me that delta V1 had to be the same as delta V total. But I could have gone the other path instead. If this is 12 volts, 12 volts, 12 volts, 12 volts, 12 volts, 12 volts, now I've got to change. Now I'm 0, 0, 0, 0, and 0. So the voltage drop across this is also equal to delta V total. So when I connect things in parallel, the assumption that I can make is that the voltages in parallel must always be the same, right? They all have to have the same voltage no matter what. Now, what about the current? How will the current change for each of these two geometries? So in this case here, I'm going to have a certain amount of current coming out of the battery. So imagine I've got a bunch of traffic coming out of that battery. Now, right here, you get an intersection. You get a junction. And that's something we didn't have in the series circuit. There were no junctions there. There were no splits. But now what's going to happen is I've got a certain amount of traffic coming this way. And imagine this is, I don't know, 10 amps, right? Or 10 cars per second coming out of the battery. Now, if I have 10 cars per second coming out this way and 2 cars per second coming out this way, what happened to the other 8 cars? Where did they go? They must have gone the other way instead. So the conclusion that I can draw here is that because all the current has to go someplace, if I know how much current goes this direction, if I call that I1, and the current that goes this way, I call that I2, well, by God, if you add those together, it better add up to I total, right? If it doesn't, then it means that you had some current come out of the battery, get to that intersection, and vanish. And that cannot happen, right? Charge is conserved. The electrons don't just disappear. And that tells me that these currents better add up to that current. So I still know that delta V equals I times R. So if delta V equals total equals I total times R total, delta V1 equals I1 times R1, delta V2 equals I2 times R2. All those rules still apply. Let's rearrange this. I can write that I total is going to equal delta V total divided by R total. And I can do the same trick for the other two as well. I1 delta V1 over R1 I2 equal to delta V2 over R2. And what I can then do is, since I total equals the sum of those things, I can say that I total, that's delta V total over R total, has to equal I1 plus I2. So I1 is delta V1 over R1 plus I2 is delta V2 over R2. And oh, look, all three of these V's we said were the same. And if that's the case, they will all cancel, leaving behind 1 over R total And of course, if I had a third branch with an R3, I could just keep going. So this is my equivalent resistance rule for resistors that are in parallel. And if you've been paying attention, you'll recall that when we did capacitors in series and in parallel, we had a very similar set of rules. It was the same two rules, except they were backwards. So for capacitors in parallel, you just added them. For resistors in parallel, you have this little reciprocal type rule. For resistors in series, you just add them. But for capacitors in series, you have the reciprocal type rule. So it's the same two rules, they're just backwards. They're swapped. So make sure that you keep them straight in your head. Otherwise, hilarity will ensue. So far, so good. We can do this in our sleeps. Let's make it more complicated. So let's imagine that I've got some big, nasty, ugly circuit, but it's a DC circuit. So what's going to happen here? Let's imagine this is 100 ohms, 50 ohms, 75 ohms, 120 ohms, 200 ohms, all connected to a 12-volt battery. So what's going to happen in this circuit? Well, one thing that I did was I built in a short circuit into this particular circuit just to see what would happen. So imagine each of these were light bulbs. When any of these light bulbs light up, and if so, which ones would light up? You don't know, Tom, because we're not paying attention.
It's not the no. I don't know. To be honest, I'm not even gonna hold you.
Okay. So let's think this through, right? Do I have a complete circuit? Will there be any current coming at all through that circuit?
Yes.
Okay. So some of them will light up. So current's going to come out of here.
Mm-hmm.
It's going to definitely flow through this guy. It's going to get here. It's going to split two ways. Some current's going to go this way and this way and back. So these three would all light up because they'd all have current going through them. Now, I'm going to have current go through here, and it has a choice. It could go through here and back, or through here and back. So stuff's going to light up, and the big question, I guess, is what's going to happen right here? So in order for me to simplify this circuit down, what I would have to do is to use the rules for series and parallel and determine what the equivalent resistances would be. Does that make sense?
Yes.
And I'd be looking for things that are in series or in parallel with each other.
The 50 and the 12. Is that 50?
That's a 50.
Oh, okay.
That's a 120.
Oh, 120.
Yeah. So you might think that the 50 and the 120 are in parallel, right? Because they're side by side, but they're not.
Okay.
And the reason that they're not is because if I go through the 50, I don't just go through the 120. I got to go through the 75 also.
Okay.
But the 75 is not in parallel with the 120 because I could go through both of those, but I don't have to go through both of those. I could go through this and here instead. So I can't combine the 50 and the 120 till I deal with this guy. And I can't deal with this guy until I deal with this thing.
So the 75 and 120 is in twos.
Well, they would be, except that if I go through the 75, I don't have to go through the 120. I could go this way instead.
Oh, okay.
So even that's too complicated. And so I'm choosing this as an example because what I want to think about is what's going to happen in this little part right here, right? This is the part where I have a short circuit. And this is tricky because normally you wouldn't even worry about this because there's no resistors there. But I'm going to kind of imagine that this is like a resistor whose resistance is 0. That's what I'm going to treat this whole branch as a resistance of 0. And I want to see what's going to happen inside this section here if I combine those two things together. Does that make sense?
Yes.
Well, if I do that, if I treat this branch as a resistor whose resistance is 0, I would have 1 over R total is going to equal 1 over 120 plus 1 over 0. So when I solve for R total, what do I get?
1 second. I got an error. Am I not doing something?
Well, you just divide it by 0, right?
Oh, yeah, you can't do that.
You can't divide by 0. So your calculator's like, dude, you can't do that. Now, what does that mean in physicsy terms? Well, you can't divide by 0, but you could divide by something super, super close to 0. And what you'll find is if you divide by something super, super close to 0, the smaller that number is, the closer to 0 you get, the bigger your thing is. So dividing by 0 is basically like infinity. So I have 1 over 120 plus infinity. Well, infinity plus anything is infinity. But that means that R total is 1 over infinity. But anything divided by infinity is 0.
Mm.
Does that make sense?
Yes.
No, I know.
So what's going to happen is this thing right here is like a 0 resistance. It's like that 120 is not even there. And in fact, here's what's going to happen, right? When you connect this circuit up, when the current gets to this little intersection, the electrons have a choice. They could go this way and have to do some work to get across. Or they could go the other way and not have to do any work. So what's going to happen is, in other situations, like when I get to this intersection here, some of the electrons are going to go this way and do some amount of work. Some are going to go this way and do a different amount of work. What's going to happen is you'll have some electrons choose each path. It's kind of like when you drive to work in the morning, right? There's oftentimes multiple ways you can get to work. I remember when I used to live in Mint Hill, one way I could get to work in the morning was I could drive down Independence Boulevard. And if I did that, it took me about 20 minutes to get to work, provided that traffic didn't suck, right? But some mornings I'd listen to the traffic report and find out, oh, there's an accident or something, and traffic is backed up on Independence. And I knew that during those mornings, if I, got on Independence, I could be late. And so I needed to find an alternate way to get to work. Well, I had a series of side streets that I could go through to get to JCSU. And I knew that series of side streets, I had a lot more stopping and going. And it usually took me about 40 minutes to get to work. However, the good news there is that it never backed up. It was always 40 minutes, whereas Independence, when it got backed up, it could be like an hour or two if things got really bad. So, what would happen is every morning I'd, get up and get ready to leave with at least 40 minutes, I'd listen to the traffic report. And if the traffic report said that Independence was clear, I'd take Independence and get to work and have 20 minutes to spare when I got to work. If the traffic report read that there was an accident or something, I'd take the alternate route. I'd get to work 40 minutes later, but I'd still be just barely on time and everything would work out great. So that's kind of what the electrons are doing here. Is like they get here and they're like, man, I could go this way, but if everybody went that way, there'd be a traffic jam. It'd be too slow. So some of them will go this way and then the rest will go the other way. Well, here what's going to happen is they get to there and they have that same choice. This is the easy way. That's like the 20-minute route. And they'd rather take this route than the crappy slow down route. And in fact, because there's zero resistance here, this way never backs up ever, which means all the current will take this easy path and nobody goes this way. So what will happen if you tried to hook up a circuit like this with a short circuit? This light would not light up at all, because all the current that could have gone down this way would instead choose to go through the zero resistance path. Now, the other lights, they would be on normally. They might be drawing more current than you'd expect because there's extra current going through here, but that's what will happen. So sometimes in your household, if you have a short circuit, what may end up happening is like a particular bulb or a particular outlet, that light may go out. And it's because all the current that would have gone through that light has found some other way to go through something that it's not supposed to and bypass the light. The effect is that it creates a zero resistance here. It may not kill everything, but it will for sure not power whatever it is that's connected to that short circuit. Does that make sense?
Yes.
So that was the thing I wanted to point out, is like, what effect does a short circuit have? Basically, you put a short circuit there and it's like the other parts that are being shorted out, they might as well be gone. I could take this out of the circuit and it wouldn't change my answer at all. And in fact, now that I know that, I could just redraw this with this whole section replaced by a resistance of 0. Was there one on the bottom? There was. So this is the part that used to be the 120, but I've replaced that entire thing with a resistance of 0. So now, when I go to break things down, I've reduced all of that to 0 resistance. What happens next? What do I combine next? Could you find two resistors
sorry.
in parallel?
You can do either or, right? Because the 100 and the 200 is parallel, and then.
So you say that the 100 and 200 are in parallel, but why do you say that? By what basis do you make that judgment?
I literally just look. I know you said not to do that, but I literally just look at it from being across from each other.
You're like, oh, they're across from each other. Yep.
Yeah.
And the reason I say not to do that is because sometimes, like right now,
the
that'll send you the wrong way, right?
Yeah.
There's a reason I'm drawing the circuit like this, is because I'm trying to trap you. Right? I'm trying to show you that sometimes if you think, oh, they're across from each other, that means parallel, it'll mess you up. And this is one of those times. Because to be in parallel, if I go through one, I can't go through the other. But look, if I come out of this circuit, I'm going to go through that 100 no matter what, right? But then I'm going to go through either this guy or this guy, and I'm going to get to the 200. So anything going through the 100 will also go through the 200. So there's no choice. They're not in parallel.
Okay.
So what is in parallel? Is there anything in parallel?
The 175.
So to be in parallel, I have to say that I go through one or the other, but never both. But here I am, I'm coming out the battery. I went through the 100.
Mm-hmm.
And then if I go this way, I'm going to also go through the 75.
Mm-hmm.
So the 100 and the 75, they can't be in parallel either because I could, in principle, go through both. Are the
It's
100 and the 75 in series?
you said are the 100 and who?
Well, we tried the 175 and to see if they were in parallel, and we decided that they weren't because I
They
could
are
go
in
through the
series.
100 and the 70, but are they in series?
I feel like all of it is in series.
No, for two things to be in series, I have to be able to say that if I go through one, I for sure go through the other one also. And I can't say this is in series with this because I could go through the 100 and then the 50 and never go through the 75. So these guys aren't in series because I have an alternate route.
So the 50 and the 75
The 50 and
or
75 are what?
all in series?
Well, if the
Or
50
no?
and 75 were in series, I'd have to say that if I go through one, I must go through the other. Is that true?
Oh no.
So they're not
What?
in series.
This is confusing.
I know, that's why we're doing it.
Okay, so you said series is you have to go through the other one, right?
Yeah, if you go through
Okay.
one of them, you have no choice. You must also go through the second one also.
So
The first square, or the first 100, and then the 50 are in series, but it's also
and
in
the
series.
200.
The 100 and the 50 are not in series because I could go through the 100 and then also the 75 and never go through the 50.
Could go through the 100, but
Don't have to go through the 50.
so 50 and 200.
So could I go through the 200 but not go through the 50? Well, if I went around this way, I went through the 200 but I didn't go through the 50.
Oh Lord.
Okay, Dr. Fleming, here we go.
I don't know this. Okay,
All right,
no,
all right.
no.
Look,
So look,
blank.
this is why it's tricky. The ones that I'm going to have to combine first aren't in series; they're in parallel. But the two that are in parallel are the 50 and the 75.
How? Okay, so the
So
parallels.
imagine you're right here, right?
Okay.
You have two choices, right? I could go down through the 50 and end up right here. Alternately, I could go around through the 75. I'll end up in the same spot.
So the parallel is what is it again?
Parallel is about having two choices. You go through one or the other. You
Okay.
end up in the same place, but you don't go through both.
Okay.
And that's what's happening here is I go through the 50 or I go through the 75. Either way, I end up in the same place. So the ones that are in parallel are the 50 and the 75. And I know it's weird because they're not side by side. I did it on purpose, right? They're not side by side, but they're in parallel. So what I'm going to do is I'll first combine these guys. And, you know, the reason we spend some time on this stuff is because there's kind of an art to it. It takes practice to recognize what you simplify when. And it can be confusing, right? The thing you have to do is you have to go back to basics and, you know, remember the definition of being in series, remember the definition of being in parallel, and just, you know, try those until you find things that work. So I'm going to combine these. If I call this 1, 2, 3, and 4, then 1 over R, 3, 4 combined will be 1 over R3 plus 1 over R4. So that's 1 over 50 plus 1 over 75. That's easy enough to get a common denominator. That's 3 over 150 plus 2 over 150. Which is 5 over 150. And 150 over 5 is exactly 30 ohms. So these guys together are like, how to get what?
I didn't get that. Is it because I'm doing it on the calculator?
Possibly. So,
Okay.
I mean, I did this because I can do that in my head without having to think too hard, right? I know that 50 times 3 is 150, and I know that 75 times 2 is 150. So I just did common denominators to make it super easy because 3 plus 2 is 5.
I did it wrong. I got it.
Yeah. You know, if I was doing this on my calculator, and again, you don't have to use common denominators. So look, I'm doing this on my calculator,
Mm-hmm.
and you've got this nifty little reciprocal button right here, the x to the minus 1 button.
Mm-hmm.
So if I'm doing this, I'm going to be like, okay, I've got 50 reciprocal plus 75 reciprocal. Boom. Now, that's 1 over my thing. It's not R34, so I got to take the reciprocal of that. So reciprocal of that.
Okay.
So don't feel like you have to do the stupid common denominator stuff. I see a lot of students struggle with that, and they freak out because they're terrible with fractions. Don't. I do it because this one was obvious enough that I immediately saw how to do it, and I knew I could do this in my head in less time than it would take me to pull my calculator out. But if it's not obvious, just put your calculator.
Okay.
Zoom out. There we go. All right, so super easy. We've combined all these together, and now it's a 30. Now, if I treat this as one big resistor, I come out of the battery, I go through the 100 for sure. Then I go through this thing for sure. Then I go through this thing for sure. So this, and this are in series now. And so our total for the whole thing is going to be 100 plus 200 plus 30. So this circuit has a total resistance of 330 ohms. So far, so good?
Mm-hmm.
Yes,
All right.
I'm following Dr. Fleming. I'm here.
All right, I like it. So at this point, let's figure out something with this circuit. And remember, the original circuit was the slightly more complicated. We got this guy over here, this 120 over here, right? Let's figure out the power being delivered to each resistor. Now, how do we find power? Remember, we had 3 formulas, right?
Mm-hmm.
I times V, or I squared times R, or V squared over R. Now, when I put this particular problem on exams, there's always somebody in every class who sees a circuit like this, and I say, oh, find the power delivered to the 50 ohm resistor, or something like that. And what they will do is they'll be like, okay, well, power is V squared over R, and V is 12. Aha, V is 12. And R is 50. Aha, V is 50. So they'll go 12 squared divided by 50 and get an answer, and it's wrong. How come? What are they getting wrong?
I forgot, but I know what you're
They
talking
didn't
about.
do that before. They didn't find the total resistance. They just
Well, even if they did find the total, maybe they'll be like, oh, I'll find the total resistance 330. So the V squared over R, so V is 12 and R is 330. And the answer is 12 over 330. Why is that wrong?
Because they're not finding the power that's coming from the 50, right?
Aha. So if I were to go and find our total, get 330, and use 12 volts squared divided by 330, that would be a power, but that would be the power to everything, because I took the voltage for the whole battery and the resistance for the whole circuit. That's the total power coming out the battery. But what's going to happen is some of that power gets delivered to this guy, some of it gets delivered to this guy, some of it gets each resistor is going to get its own fraction of that power. So if I do 12 squared divided by 330, what is that number? 144 divided by 330. That's 0.436 watts. Well, the power coming out of that battery is 0.436 watts. But what's going to happen is the power going to that 50 has to be less than that, right? Because that
Mhm.
1.436 watts gets shared by everybody.
Wait, Dr. Fleming, how did you get that?
So if I took P equals V squared over R, and I went V squared is 12 squared over 330. So I took basically V total squared over R total.
Okay.
But that's going to give me P total. That's the total power for everything. Right? So if I did the 0.436 watts, that's all the power coming out of the battery. But that tells me that the power for each of these things is going to be less than that. And if I want to define how much power went to each one, then what I'm going to have to do is I'm going to have to find not V total, but the particular V across just that one guy. Remember, if this is 12 volts, I'm going to drop some across the first resistor. I'm going to drop some more across the second resistor. I'm going to drop some more across the third resistor. And this V plus this V plus this V better add up to 12.
Okay.
Does that make sense?
Mhm.
So that's where a lot of people go wrong, is they forget that each resistor is going to have its own voltage drop, and it's going to have a voltage drop that will be smaller than 12. So in order to solve this problem, I'm going to have to figure out those individual drops, not the total for the entire circuit. That's where many, many students go wrong. So here's how we're going to do this. We found R total for the entire circuit, and I know or V total for the entire circuit. So what I'm going to do is I can find, since I know that delta V total has to equal I total times R total, I can then solve that for I total. This is going to be all the current that comes out of the battery. So 12 divided by 330. It's 0.0364 amps. That's how much current came out of that battery. You with me so far?
Mhm.
Now,
Yes.
in my original circuit, I had resistor 1, 2, 3, 4, and don't forget the 120 that I scribbled out here.
Mhm.
We'll call him 5. Right? Now, what's going to happen is, once I know how much current comes out the battery, the next step in every problem is to look back at my original circuit and ask myself, are there any resistors that I have no choice but to go through?
1.
Yeah. Any current that comes out of the battery has no choice but to go through resistor 1. That means that any current coming out of the battery, this much current, must go through resistor 1. So if I'm keeping track of all the different currents that I've got, I've got 5 different currents to keep track of. I1 for sure has to equal I total. If I could just go ahead and fill that blank in right now. Now, it's not the only one.
Wait, you said I1 equals I total. Oh, okay. No.
Yeah, because anything coming out the battery, that's I total. We know how much comes out the battery is this much, right?
Mhm.
If it comes out the battery, it's got to go through resistor 1. So that means resistor 1 has to have that much current.
Okay.
Is that the only one?
I want to say 3, but I don't know.
So do I have to go through 3? Could I get through the circuit without going through 3?
Yeah, you could.
Yes.
Right. That means that resistor 3 is going to have less current than I total.
Okay. Um, what about 2?
Yeah. Yeah, there's no way to get back to the battery without going through 2, right?
Mm-hmm.
It's because of where it is in the circuit. So resistor 2 is going to have the same current also. So now I figured out of my 5 currents to deal with, I know 2 of them. Now, the good news is Ohm's law says that V equals I times R. So I1 should equal, or I1 is this, V1 should equal I1 multiplied by R1. And since I1 we figured out, and R1 was 100, if I take this times 100, I get 3.64 volts. I now know the voltage drop across resistor 1.
Mm.
By the same reasoning, V2 is going to be I2 times R2. That's going to be 7.28 volts. Right? Because R2 is 200. It's literally double what that was. Are so good?
Mm-hmm.
So now let's look back at the original circuit. Now, I got 12 volts right here. And according to our math, when I go across this resistor, I'm going to drop voltage by 3.64. So I started with 12. I've lost 3.64. So 12 minus 3.64 leaves behind 8.36 volts. I have 8.36 volts when I get to here, right?
Mm-hmm.
Now I'm going to drop across here some more and have less than 8.36 volts. Then I'm going to drop across here and I'm going to lose another 7.28 volts. But when I get to here, I got to be back to 0.
Mm.
Wait a second. How much did I lose here?
Can't you just subtract those 2?
Yeah, if this voltage plus this voltage plus this voltage better add up to 12, and I know these 2 voltages are this, then this must be the rest. So if I subtract the 7.28, I'm left with 1.08 volts. I must have lost 1.08 volts across resistor 3. So I just figured out that resistor 3 is 1.08 volts. Because I know that this plus this plus this, if I go around through this, this, and this, these 3 have to add up to 12. And I know 2 of them, so I subtracted those 2 from 12, and whatever was left must have been V3.
Wait, how did you get the 1 point? What
So
did
I
you
took
subtract again?
so I took 12 minus 3.64 minus 7.28,
Oh, okay.
and it was what was left over. You with me?
Yes.
Awesome. Except wait a second. Now what's going to happen is I know this voltage, and I know that V3 equals I3 times R3. V3 I know, R3 I know, I3 therefore must be V3 divided by R3. So 1.08 divided by 50.
0.0260.
Right?
Mm-hmm.
So now I know how much current went through resistor 3. Now wait a second. Let's go back to my circuit for a second. Now, all the current in the circuit comes in here. So right here, I've got 0.0364 amps coming in, right? Then going this direction, I have 0.0216 amps. Now, any current that didn't go this way must have gone this way instead. Does that make sense?
Wait, do that again.
So look, all the current in the battery comes out here and it gets to this intersection right here.
Mhm.
I know how much current came this way because that's I total. That's the 0.0364 amps I total, right?
Mhm.
But then the traffic splits. Some of the traffic goes down this way. I know how much traffic went that way, but all the traffic that didn't go this way must have gone this way instead. Does that make sense?
Yes.
So how much traffic went that way? What will I4 be?
Do you do the 12 minus
Well,
the first current? Or
well, not the 12. That's a voltage. So this current minus this current should equal that current. So I'm taking 0.0364 minus 0.0216, and whatever is left over must be the stuff that went through 4.
Okay.
Which is when I subtract that out, 0.0148 amps.
So you said we subtract.
I looked at the picture and said, aha, the current, the I going through number 1 comes into that intersection. So I had 0.0364 amps.
Uh-huh.
And I knew that the current going this direction through resistor 3 was 0.0216 amps.
Okay.
So whatever current was left had to go through the other direction. So I subtracted the current coming into the intersection from the current that I knew came out one direction, and that left behind this.
Okay.
Does that make sense?
Mhm.
Yes. Could you? I couldn't see the number. Well, I'll go ahead and subtract it. Oh.
Yeah.
0.0148. Okay. Great.
But wait a second. If I know I4 and I know R4, V4 should equal I4 times R4. That's this number times R4 is 75. I get 1.11 volts. The fact that I'm not getting 1.08 suggests that perhaps that's a round-off error.
You're supposed to get the same number?
They should be.
Oh.
You'll see why here in a minute. Now, wait a second. Let's go back to my circuit. We said that if you go around the loop, all the V's better add up to 0. So here's 12 volts, right? I go across resistor 1, and my voltage is going to drop by 3.64 volts. Then I'm going to go across 4. It's going to drop by 1.11 volts. Then I'm going to go across this, and it's going to drop by an unknown number of volts. Then I'm going to go across this. It's going to drop by 7.28 volts. Except when I take this plus this plus this, this plus this plus this, adds up to basically 12 already, which means there's nothing left for it to drop across this guy. V5 has to be 0. But that means that I5 has to be 0, which we already figured out because it was a short circuit. Now, I'm kind of playing a little fast and loose because you'll notice for the way that we rounded here, 3.64 plus 7.28 plus 1.11 actually equals 12.03. Not 12 exactly, it's 12.03. Well, why is it 12.03? Because what happened was we rounded this number and then subtracted those two numbers, so this number is a little bit squishy, which means this number is a little bit squishy. And in fact, this should have been that, because V3 and V4 are in parallel.
Okay.
Yeah. So, yay, we just figured out all the currents and all the voltages. And so if I wanted to know the power being delivered to each of my resistors, I could do any of my 3 power formulas. right? So how much power does this guy get? Well, I could do I times V. So I'll do this I times that V. So that guy, power 1 was 0.1325 watts. I just took this times this. The power for 2 would be this times this, which is 0.264 9 watts. The power through 3 would be this times this. Point 0.2332. Let's keep extra sig figs. The power through 4 would be this times this. So 0.01598 watts. And of course, the power through 5 is just flat out 0. And notice what we had said earlier was that the total power for everything ended up being 0.436 watts. Well, these are the powers for each of the individual resistors. And if I take this plus this plus this plus this, so 0.1325 plus 0.2649 plus 0.02332 plus 0.01598, you can see that the amount of power that I get is 0.436. So the total power for all of them added together just happens to add up to what we said the total power had to be to begin with. So yay, math works. Super easy. We can do this in our sleep, right?
So for this problem, wait, can you go back to the other page?
Mm-hmm.
So we needed to find the power for 3, right?
Yeah, I think I originally said, well, let's find the power just for the, well, originally I said find the power for all of them. But
Okay.
a lot of times, like on an exam, I might just ask for the power for one particular resistor. So, the power for 3 was just this one resistor.
Okay.
But I could have asked for the power for any of them. We found them all, right?
Okay.
And we found that if I added up all the total power, it did in fact add up to, the P total, which was just V total squared over R total. We got the same number from that as we got by adding all of them together, which just shows you that, it still works.
Okay.
So the process for these kinds of circuit problems, anytime I have like a simple circuit like this with a bunch of resistors, my technique is always the same, right? Step 1, the first thing I'm going to do before I even worry about what question they ask me is I'm going to find R total for everything. I'm going to simplify everything down until I get R total. Then what I'm going to do is I'm going to figure out, once I know R total, I'm going to figure out how much total comes out, how much current comes out of that battery. I'm going to find I total. Then once I know what I total is, I'm going to go back and look at my circuit, and I'm going to ask myself, do any of these resistors have to have I total go through them? They don't necessarily have to have I total, but in many cases, there will be at least one. Here, there were 2 that had I total go through them. And if that's the case, I could just fill those blanks in right off the bat. Now, once I know the current through a resistor, I could find the voltage drop across the resistor. And from there, what I'm going to do is I'm going to rely on the fact that all the voltages have to add up to V total around any loop. to start filling in additional blanks. Once I knew that this plus this added to 12, and I knew these two, if I subtracted that from 12, whatever was left was this. Once I know what this voltage is, I can find that current, and I'm just constantly looking for ways to fill in a blank until everything is done. That is my technique for every simple DC circuit that I will throw at you. All right, that's it for today. Just a reminder, exam 1 is going to probably go live sometime on Thursday. It will cover chapters 18 and 19, but not 20. So this is not on the exam, but capacitors, which use a very similar technique. So the rules for equivalent capacitance and equivalent resistance, or for series and parallel, you should know. Resistance, not so much. Don't get them backwards. But that'll go live sometime on Thursday, and we'll probably do Friday night at midnight.
Is there any like software that we need to download or anything?
Yeah, you're gonna have to do the Respondus lockdown browser.
Okay.
You can get that link. It's on Canvas.
Okay.
So yeah, make sure you've downloaded that. I'm gonna try to get a tech test, like a fake assignment that you can sign in on just to make sure everything's working right.
Mm-hmm.
So that the idea is that you'll do the fake assignment, make sure that everything works before you try to log into the test. I'll try to post that sometime tomorrow.
Okay.
I'm going to try to make sure I know how to set it up later this afternoon. But that's my timetable for this.
Could I download that on my phone? I can use it on my phone.
I don't think that it works for your phone, Tamisha. Is that the only hardware you've got?
Yeah, my computer's still down.
All right. We'll figure something out for you.
Okay.
We may have to do something else. I just, I hate having to rely on these stupid tech measures, but last semester, especially my 241 class, I gave out I had 13 students, and out of 13 students, 7 of them cheated.
Oh wow.
Like, seriously, guys. It was really, really obvious too. Like I had like ironclad, I can prove that you've cheated, I can prove that it's you. They all fessed up because they were busted.
No, Lord.
Weren't they on camera?
What's that? Well, no. See. So for the spring semester, because it wasn't wasn't originally an online class. We were told that we shouldn't use those sorts of tech tools because the students signed up for the class not knowing that they would need them.
Yeah.
Whereas like this semester, you knew it was online when you signed up, so that's why I feel freer about requiring more of that stuff. But there, it was like, guys, here's an exam. It's open notes, open book. Just don't go to any external sites.
Mm-hmm.
Right. And then, I put the exam up, and within a few hours, I'm searching on Chegg, and they were stupid for posting my exam questions to Chegg because what kind of people answer the questions on Chegg and Yahoo Answers and that kind of stuff?
Yeah.
Professors, right? Right. Who's giving you
I'm
those
not
answers?
playing with them.
Right. So yeah, I look there and I can find all these numbers, and of course, everyone has a different version of the exam.
Right.
So it's like, I know you're the only one who got this question. It was you. You're busted.
Yeah.
So yeah, and you will find that each of you will have different exams. So don't even try it, because I guarantee you, like if Amaya logs in and she posts her question to Chegg, and Tamisha's like looking on Chegg trying to find it, she might find Amaya's question, but her questions won't be the same.
So is it still open note or no?
It'll be open notes. Feel
Okay.
free to use your notes all you want. I can't stop you from doing that. But I am going to lock your browser down. And the camera, there'll be the stupid camera there just so that you're not on your phone on a separate device or something. I should be able to check for that. So
Okay.
but that's how that'll play out. All right, guys. I will talk to you guys tomorrow.
Are you gonna be in your office hours today?
Yeah. If you guys, I'm in my office hours every afternoon after 1 o'clock when my class gets out.
Okay.
So just shoot me an email and I'll set the Zoom up.
Okay.
So.
Okay.
Yep.
Thank you.
Have a good
You're
day.
welcome, guys. Have a good day. Take care.